Alrighty, lads and ladies, welcome back to the wonderful world of calculus. Last time, we introduced the idea of studying the derivative as a function in its own right. Today, we're going to play around with those ideas just a little bit more, and then we'll inch forwards towards learning our first few differentiation rules, which is a big deal. It's a fun thing. I want to ease you into the differentiation rules, because what I don't want to have happen is anybody who hasn't solved the existing homework problems learn the differentiation tricks or rules that I'm going to teach you and then never apply the limit definition to the existing homework stuff. So I'm hesitant to get into chapter 3. That's what I'm saying. So chapter 3 is good stuff and I'm excited to show it to you. But it's very important that you solve the chapter 2 problems using the chapter 2 methods. And I think somebody, maybe it was Seth, I don't remember, somebody asked me in class last Friday, if we know the differentiation tricks, can we use those on chapter 2 problems? The answer there is yes, you can use them to arrive at the right answer, but no, you will not get credit if you do that on a test where the problem says use the limit definition of the derivative. So let me, I don't have your syllabus open. Let me pop up your syllabus, because the other thing I want to talk about a little bit is the first test. The first test is coming. It's almost here. Here we are. So we have talked about rates of change and the derivative as a function a little bit. I want to talk more about this. The next topic is the chapter 3 thing, the basic differentiation rules, and I am going to give those to you today. But I just want to emphasize, because I know there are still people back working on the chapter 2 homework, and that is fine. It's okay. But it is necessary that you get comfortable working with the derivative as a limit. So all of the problems in this homework set, 2.7 and 2.8, you need to work them using the limit definition of the derivative. So when they say find the slope of the tangent line at the point 1, 7, you need to apply the limit as x goes to 1 of f of x minus f of 1 over x minus 1, or the limit as h goes to 0, f of a plus h minus f of a, and then send a, and then plug in 1 for a. All of those problems really do need to be solved that way. You need to practice those. The same thing's true here, right? Where you find the equation of the tangent line. In order to get that slope, you need to be taking the limit as x goes to 81 of square root of x minus the square root of 81 over x minus 81, and making sure you're comfortable with, with how to do that. So before I dive into chapter 3 today, which we are going to do, I want to solve 1 or 2 problems like this to be very, very clear about what's expected of you on the test. And then the other thing I wanted to do was to look at one more application problem, because we only had one of those like real world rate of change problems from last week that we were able to do during class. And I think number 8 here in the homework is a nice one to talk about the derivative. These things are all very much like what we did in class, and we were detailed about that, so I'm fine with that. Maybe I'll take this guy 19 and do him carefully. I think that's a little closer to what we're talking about. So 2 things. First, of course, this is MAC2311, section number 004. That is calculus 1. And the date today is the 24th of January, 2022. Today, we're going to do a little more practice with rates of change and the limit definition of the derivative. And then the other thing we're going to do is we're going to begin chapter 3 on differentiation They call them rules. Tricks, formulas, rules, whatever you want to call them. That's what we're doing. So for example, I could ask you on a test to use the limit definition, I'll abbreviate def, of the derivative to find the equation of the tangent line.
Professor.
Hey, Professor.
Oh, are you guys not seeing this?
Yeah.
Sorry. Thank you. All right, yeah, MAC2311, section 004, calc 1, 124.22. Today we're doing these things, right? Practice with rates of change and the limit definition of the derivative f prime. And then we're going to begin chapter 3 on differentiation rules. Sorry, I'll give you a second to write. Beautiful day out today. Okay. So this is the exact sort of problem I could ask you on a test. And the way I solve this is how I expect you to solve it on a test. Right? Specifically here saying use the limit definition of the derivative means do what I do here. So we could try to find the tangent to f of x equals the square root of x at the point where x is equal to 81. And big picture, our strategy, we need two things. In order to find the equation of any line, you need a point and a slope. The point is always the point of tangency. That's the point where the tangent line is tangent to the graph, right? The point where that tangent line just kisses the graph. Since we're trying to find the tangent line at x equals 81, that means this is 81 comma f of 81. And since f of x is the square root of x, that's 81 comma 9. That's our point. The slope of the tangent line is the fun part. That's the derivative evaluated at that x value. And there are two ways that would be acceptable to come at this guy. We have two limit definitions we could use, right? The x to a definition and the h to 0 definition. So the blue here, you would not need to write as a part of your solution, but the definitions, if f primed of a is limit x goes to a, f of x minus f of a over x minus a, or limit h goes to 0, f of a plus h minus f of a all over h. What we saw last time, one of the things we saw last time was that these two definitions are equivalent. They're just two different ways of taking limits of secant slopes to get tangent slopes. And a here would be 81. You could crunch either of these out in general, leaving a as like a variable and then plugging in 81 at the end, or you could plug in 81 for a right at the start. It makes no difference. If you thought you might want to go on to do further things with this function, then finding the formula for f primed of a in general is the nice thing to do. If you know that all you want is the slope of the tangent line at this one point, then you can plug it in right from the start. The limit is not made any easier by plugging in at the start. It's not made any harder by waiting until the end. So what I'll do here is say that f primed of A is the limit as, which one do we want to use? We've had less practice with this one. Let's do this one, the h to 0. F of A plus h minus f of A all over h. And I'm just going to leave A as A. So I'll get a formula for f primed of A, and then I can plug in 81 at the end.
I have a question.
Yeah.
Is there a specific circumstance where one or the other should be used, or can you interchange them regardless?
They're interchangeable. If you're going to plug the number in right at the start, oftentimes this feels a little more natural. And plugging the number in right at the start here sometimes, for whatever reason, gives people heebie-jeebies. I don't know why. But no, literally interchangeable. As long as you're comfortable with the algebra in both, they're completely interchangeable. Here you'll have an A plus H trapped inside your function, and you don't have that here. So some people find the algebra easier to work with here. That's why your book uses this one first, but they are literally equivalent.
Thank you.
Yeah, of course. So my function is square root of x. So f of A plus h is the square root of A plus h. F of A is the square root of A. And h downstairs is still h. If you try to plug in 0 for h, of course, the bottom is 0. That's a problem. So I can't do that yet. Does anybody remember the algebra trick that we need to handle limits like this, where you've got a square root minus a square root?
Would you go ahead? Sorry.
I was going to say, is it the conjugate where you times them times the numerator and the denominator by the inverse, not the inverse, the.
That's it. Yeah, we multiply top and bottom by the conjugate of this expression, which is the square root of A plus h plus the square root of A. So I'll multiply top and bottom by that. And when we do that, we remember that the tops and bottoms of fractions are always in parentheses. So we got a FOIL. And while it might look nasty, this top is actually really nice. I'm going to continue over here. So this is equal to the limit as h goes to 0. I'll draw a big fraction, and downstairs I know I'm going to have h times square root A plus h plus square root A. Upstairs, if you take your firsts, that's root A plus h times root A plus h. That's just A plus h, right? The square root of something times the square root of that same thing is the thing. It's root A plus h all squared, or just A plus h. The outer is root A plus h times root A. And the inner is negative root A times root A plus h. So the outers and the inners cancel. And that's what's so nice about this multiply by the conjugate trick. And then our lasts are minus root A times plus root A, which is minus A. Of course, the plus A and the negative A eat each other up. I'll write it in a separate line here, but you can probably see that the h's will cancel. That's what we wanted. And I get lim h to 0, 1 over root a plus h plus root a. And sending h to 0, now that the h is gone from the denominator, I can do that. I get 1 over root a plus root a. Which is 1 over 2 square roots of a. So the derivative of the square root function, I'm just gonna, is 1 over 2 times the square root of, if we were thinking of the variable as x, it would be x. Here, if we've left the symbol as a, that's fine. Which means that the slope of my tangent line, remember, is f primed of 81. So I plug 81 into this. This is f primed of a. So f primed of 81 is 1 over 2 times the square root of 81, which is 1 over 2 times 9, or 1 over 18. And now all we have to do is use our point slope form of a line. I've got my point, 81, 9. I've got my slope, 1 over 18. So the tangent line is y minus y0, which is 9, equals m, which is 1 over 18, times x minus x0, which is 81. And you can leave your answer like this. You do not need to put it into y equals mx plus b.
On the test, are you going to want certain like word notation that we have to put in the answer?
Nah, I'm not picky about that stuff. There are places where the language you use matters, but I will be super clear about those when they show up. Now, one little thing I would like to add here, this would not be a part of the solution, right? Not something you would need on a test. What we've learned here is that if f of x is the square root of x, this guy has derivative f primed of x equals 1 over 2 square roots of x. Right? After doing this computation, f primed of a, getting 1 over 2 square root of a, we could just replace the a with an x, right? This is what we talked about at the end of class last time with that function s of t and its velocity function v of t. There's nothing special about the symbol a. We start off thinking of a as a constant. But then in section 2.8, where we start thinking about the derivative as a function in its own right, you can just swap that for an x and be like, oh yeah, that's the derivative as a function. No, so a question in chat was, do I want you to expand this? Nah, this is fine. All right. At this point, we should be really comfortable with the point slope form of a line. So I don't expect you to put it into mx plus b. The only occasions where you would have to go on and do something else with this are when we talk about applications of the derivative. There will be a time where we use tangent lines as a tool for approximating the function. And in those instances, sometimes you will want to rewrite this in a certain way. But right now, if I just ask you for a line and you give me the equation of that line, I do not care what form it's in. And this is the natural one to write down. So I would prefer it like that, honestly, but no points lost either way. Okay, so on the test, when I say use the limit definition of the derivative to do blank, this is what I mean, right? You got to use one of these definitions. If you want to leave A as A and do it like I did here, that's fine. If you want to plug in the X value that you're using right away, you can do that too. Either one is fine, but you've got to use one of these expressions involving a limit if the problem says use the limit definition.
Can I ask like a general question on the process?
Yeah.
So basically you like take the derivative, which involves taking the limit, and then once you get that, you substitute your value to get the slope, and then after that, you just put it into a point slope formula.
Yep.
Okay.
Yeah, that was sort of the procedure here. And the first two steps could be reversed. Plug in, then take derivative, or take derivative, then plug in. When you're using the limit definition, it does not matter. To kind of tie this in a little bit more with what we were talking about last time, I'd like to take a look at these two graphs. So this is no longer a part of that example, but just for fun. To remind ourselves about the graphs of f and f prime, let's graph f of x equals the square root of x, and its derivative, f primed of x, equals 1 over 2 square roots of x. So graphing is a big deal in this class. And the one thing that I loathe about WebAssign, besides it costing $100 a semester for you guys, is that it doesn't let you draw graphs by hand nearly enough. And even when it does, it's like shitty because it tells you everything right away. So the graph of the square root function the square root of 0 is 0. The square root of 1 is 1. The square root of 2 is not nice. The square root of 4 is 2. So, you know, big fat points, something like this, right? Big old fat points. The derivative, if you had to guess what this looks like, maybe you don't know what the graph of this function looks like right away. Can we make some conjectures?
Would it loosely look like the inverse if you just flipped it upside down?
Not quite. So it depends on what you mean by inverse or here. So like reciprocal, this and this are close to being reciprocals of one another, but there isn't a nice symmetry in graphs with the original function and its reciprocal. But what I can do, remember, is thinking about some tangent slopes here. So close to the origin, the slope of this little blue line segment is quite steep. And the closer you get, the steeper it gets. So the slopes here should be y values here. So in here, I would say M tan is large and positive, right? These are large positive slopes, and they get bigger and bigger as you get closer and closer to the origin. Out here, M tan is small, right? These are very shallow lines. Their slopes are quite close to 0, small and positive. So the graph of my derivative should have y values that are very large and positive close to 0, and y values that are very small and positive far away. something like this. The domain of this original is the left closed, right open interval from 0 to infinity. There is a point on the graph here whose x-coordinate is 0. The domain of the derivative and you can see this from the algebra expression or from the graph if you think carefully enough, does not include 0. Does not include 0. What we have here is a vertical tangent line. If I'm a little guy surfing along this graph, like, sliding over here to the left, as I come in towards the origin, I'm like going straight down. I don't go straight down until I get there, but I get very, very, very steep. And once I'm there, I'm going straight down. So this line goes straight up and down, which means that slope is infinite. I can show you in Desmos, it draws better than I do. Right? So if we're looking and thinking about slopes of tangent lines, as I get very close to the origin here, this graph gets very close to being vertical, right? This is a very steep tangent slope right here, yeah? And even steeper, and even steeper. And then just as you come into the origin here, we're going straight up and down. That's reflected in the fact that the derivative blows up there, has a vertical asymptote there. Because remember, the y values here are the slopes here. So the y values on this graph are the slopes on this graph. So as the slopes here get bigger and bigger, which they do as we come in towards the origin, the y values here get bigger and bigger. And the slope of a vertical line is infinite. So right there at the origin, the y value on the derivative should be infinity, but infinity is not a number. So I could ask you a fun question. Where is f of x equal to the square root of x differentiable? Well, what is the largest interval for which the derivative is defined?
0 to infinity.
Do I include 0 or no? That's the fun.
No.
Yeah, very good. No. So the answer to this is the open interval from 0 to infinity, and that's precisely what we see here, right? So even though this original function is defined at 0, it is right continuous at 0. You could even refer to it as right differentiable at 0. It's not differentiable at 0 itself. I cannot talk about the slope of the tangent line at 0 on the square root function because that slope becomes infinite. Okay, just wanted to tie those things together. Is there anything else? Yeah, let's do one more thing, and let's have it have something to do with a real world problem and rates of change. There was an example here that looked okay. 19 is fun, but we don't have units. Let me do something like this here. A man, so example, is running back and forth along a straight path. His position, which I'll call S of t, is graphed below. Here's t, and we'll say it's being measured in seconds. Here's the position, and we'll say it's being measured in meters. Okay, and let's make this like 100 meters, 50 meters, 75, 25. Let's call this 10, 20, 30, 60 seconds. All right, I may end up with a guy who runs too fast to be realistic here. Bear with me. So here's the graph of his position. These would all be at 50 meters. This is at 25 meters. No, I could have gotten away with more, right? That's not an unrealistic speed, but okay. I want to do a few things. Graph the velocity function. Answer the following. When is he moving forward? And when is he moving backwards? And let's say, is he ever standing still? Okay. So here he is over his first 20 seconds. From time t equals 0 to t equals 20, he goes from wherever he started, position 0 meters, out to position 25 meters. And then from 20 seconds to 30 seconds, his position changes from 25 meters to 50 meters. From time 30 seconds through 50 seconds, his position is constant at 50 meters. And then over the last 10 seconds, from 50 seconds to 60 seconds, he runs all the way home. So if I wanted to graph his velocity, v of t, which we know is s primed of t, the derivative, right? Velocity is the derivative of position. the time here is still measured in seconds. What would the units for V of t be? If position here is measured in meters and time is measured in seconds, then the rate of change of position is measured in what?
Meters per second.
Very good. All right. In order to begin plotting points here, in order to say any of the values of V of t, what do I need to do with the information I have up here?
Would you have to find the slope?
Exactly, exactly. His position is piecewise linear. So all of these slopes, these are constant slopes. So the derivative, for example, from here to here would be 0, because the slope of this line segment is 0. And in fact, I'm going to need to allow for a bit of negativity here, because sometimes those slopes are negative. So let me begin by marking this off in the same chunks. But the y values are going to be different y values. They have different units. Over this first time interval from t equals 0 to t equals 20, how fast am I going?
Ten per second.
It would be the 25 divided by 20, right?
Yeah, so
So let's do it over here. I'll put the calculations up here. So over this time interval, the slope is 25 over 20. And you can reduce that. Those are both divisible by 5. That's 5/4, or 1.25 meters per second. So if I mark this as like 1 meter per second and 2 meters per second, he's going 1.25 meters per second, somewhere right around there, from time t equals 0 to time t equals 20. And he is going that same speed over that whole interval. Now, right there at that moment, he's going to change speed. So I would put an open circle here. And I would also put an open circle here, because at time t equals 0, he's not yet going that speed. He starts going that speed the second I start the stopwatch.
Would your y values also be in meters or?
Meters per second down here.
Okay, I see.
Now from time t equals 20 to t equals 30, he covers another 25 meters, but he does so over 10 seconds. So slope here is 25 tenths, right? The rise over the run. And again, both divisible by 5, that's 5 halves, which is 1.5. I'm sorry, 2.5. So we're 2.5 there. Open circle here. He does this only for 10 seconds. And it's hard to see there. I know it's open there. Then from time t equals 30 seconds to t equals 50 seconds, he's holding still. The slope here is 0. So for that 20 seconds from time t equals 30 to t equals 50, his velocity function is identically 0, and we would use open circles on the ends there. And in this last time interval from 50 to 60 seconds, that slope is negative, he's going to go 50 meters in 10 seconds. The slope is negative 50 over 10, or negative 5 meters per second. So that would be down here. Okay. So this would be a reasonable graph of the derivative of that function. Right? This right here is the derivative or velocity for the position function graphed in part A. And the y values here, this was 2.5, this was 1.25. The y value here is negative 5.
Why don't they connect?
It's a good question. So what feature of this graph, what geometric feature of these weird points here corresponds to the kind of lack of connection between these pieces? What's the dude doing? Let's think about it like that first. What's the guy doing that makes the derivative graph jumpy?
Is it acceleration?
Yeah, his acceleration isn't continuous. He's changing his speed abruptly. So at 20 seconds into his run, he immediately goes from running at 1.25 meters per second to running at 2.5 meters per second. It's an instant change of speed. He doesn't gradually speed up to that. He just immediately goes from this speed to this speed, from this speed to this speed. And the same thing happens here at 30 seconds. He goes from running at 2.5 meters per second to just immediately dead stop. Like he hits a wall, he just chunk. Now, in real life, people don't do this, right? In real life, there would be a steep transition from here to here, from here to here, and all that. Geometrically, what's going on the graph is that these are pointy, right? Kind of like the absolute value graph has that pointy V. These are not joined together in a smooth way. So it's the fact that this is not a smooth transition that gives us the discontinuity in the derivative. That's a good question, and it's a neat observation. I'll add it in as a little note here. Now, the position isn't smooth, which means that the position function isn't differentiable at those points. So the derivative is not continuous. Focus is failing here. Come on, focus. There we go. So the position not being smooth means that the function is not differentiable at those points, which means that the derivative can't possibly be continuous. The derivative is not even defined at those x values or t values. We're not differentiable here. We're not differentiable here. We're not differentiable here. And we're not differentiable here.
Can I ask why it's open circles instead of closed circles?
Because if I put a closed circle, say on one of these, then I would be saying at the time t equals 20 seconds, he is going that speed. But what's really going on is at the time t equals 20 seconds, he is transitioning from one speed to another, and he does it in a clunky fashion. So he's no longer running at this speed, but he's also not yet running at this speed. So I can't nail down the value of his velocity there. Another way to do it is to ask, what would the slope of the tangent line be here? Should it still be the slope of this piece? Should it be the slope of this piece? Maybe the average of the two? There are ways to think about that, but if we're just following the definitions, this function is technically not differentiable there. So that means that the derivative cannot have a y value on its graph there. These are great questions. What else are we thinking? Okay, let's transition to part B then. When's he going forward? When's he going backwards? How about forwards first? When is he going forwards?
He's going forward. Oh, you can go.
Oh, sorry. Is it t equals 0 to 30?
Yeah, I think it's fair to say that he's going forwards from 0 to 30. Yep. If we're being very picky about it, we might want to omit the 20. But I would accept from 0 less than or equal to t less than or equal to 30 seconds, he's going forwards. Possible picky exception. At t equals 20. But of course, in real life, it's not the case that he ceases going forwards at this moment. He's just in transition from one speed to another. He didn't like turn around and go backwards. So 0 to 30 seconds is the reasonable answer. I would also accept 0 to 20 and 20 to 30 as separate intervals. When's he going backwards?
From 50 to 60.
Very good, 50 to 60. Right. So if your velocity is positive, you're going forwards. If your velocity is negative, you're going backwards. Does he ever stand still?
From 30 to 50.
Very good. Yep, he's just taking a breather here from 30 to 50 seconds. And again, you could argue about what's happening at the end points. If we were really being careful, we could use strict inequalities on all of these, but I would accept either for the physics situation, right? Because we wouldn't argue the subtleties of whether he's moving here or not yet. He's in transition from holding still to moving forwards, but it's an instantaneous transition. All right, so this skill of sketching the graph of the derivative or velocity from the graph of the original or position function, very, very important skill, right? We did it once at the end of class last time, and we've done it twice at the start of class today. So I'm hoping that that's sinking in. It's something I'll ask you to do on a test at some point. Those who have taken calculus in the past will rejoice at what's about to happen because they know that you don't always need to use a limit to calculate a derivative. And in fact, it is a terrible chore to use a limit to calculate a derivative. Maybe one last little thing before I do this. Higher order derivatives. We've said previously that the first derivative of your position is your velocity. Oh, I don't know why this is drifting in and out of focus so badly today. We've said previously that S primed is V and that V primed is A, your acceleration, right? How fast your velocity is changing. There's a special notation to connect the function A directly to the function S. If you take the derivative once of your position, you get the velocity. If you take the derivative of your velocity, you get your acceleration. So we say that A of t is S double primed of t, i.e. that acceleration is the second derivative of position. And you can do this with any function. Right? If you take the derivative, we've learned that that gives you a new function. In general, given a differentiable function f primed is the first derivative. I'll say f primed of x. Differentiable function f of x. First derivative. And it is a function. So I could use the limit definition to take the derivative of that function. And then what I get, we call f double primed, or the second derivative. You could do it again. No one can stop you. You can keep going as many times as you want. After 3, though, this notation becomes really cumbersome. I might have the 12th derivative of a function. I don't want to write 12 little primes, right? So the next notation here would be f parentheses 4, like this. That would be the 4th derivative. And you can keep going as many times as you want. If the original function is your position, s of t, then the first derivative we know is the velocity, s primed of t or v of t. The second derivative we call the acceleration, which is s double primed of t or v primed of t or a of t. Does anybody know the name for the third derivative of motion? There is a term for the derivative after the acceleration.
Momentum, maybe?
Oh, what was that?
Momentum or no?
Momentum is connected to these. Momentum is the
Is it
mass
jerk?
times the velocity. So that comes out of first derivative information. But so our position, s of t, first derivative, velocity is how fast your position is changing over time. Your acceleration is how fast your velocity is changing over time. So how quickly you are speeding up or slowing down. The change in your acceleration has a funny name. It's called jerk. When you go over a speed bump and you feel like an angry transition from that weightlessness to coming back down, that's jerk. And this is the third derivative of position, or the second derivative of velocity, or the first derivative of your acceleration. I don't think it has a specific notation, maybe j of t. I'm really not sure. After that, things just get silly. People at MIT decided to call the 4th, 5th, and 6th derivatives snap, crackle, and pop. I don't expect you to know anything besides position, velocity, and acceleration. But it is a fun fact that this next one is called snap, then crackle, then pop. I don't know the specific person that came up with these names, but clearly they like the Keebler elves. But jerk is appropriately named. It's a rapid change of your acceleration. And that feels jerky. On roller coasters, for example, when roller coasters are designed, they do take jerk into account. They do try to calculate as vectors, not just the first 2 derivatives, but the third derivative as well, to give that smooth feeling. And this is the difference between Velocicoaster and Montude, right? Velocicoaster, more modern, feels very smooth. Lots of careful evaluations of jerk derivatives there. Kumba may be a better example. Kumba, they care about your position, velocity, and acceleration, but man, does that thing rattle you. They did not do a lot of jerk calculations on that. Okay. There are other notations for derivatives besides these. I don't want to dump too much notation on you at once, but You can take derivatives of derivatives, and those are rates of change of rates of change. And the easiest way to start thinking about them is through position, velocity, and acceleration. So think about how it feels in the car. If your position is constant, you're not moving anywhere. If your position is linear, then your velocity is constant, and you're not pushing on the gas pedal down or up, you're just cruising at a certain speed. If you shove your foot down on the gas, then you are accelerating. You feel pressed back into your seat. That's a positive acceleration. That is your second derivative being a positive constant. Your velocity would then become something like a quadratic, and your position would become something like a third-degree polynomial of time. All right, we'll get into more of those examples as we dig deeper into the problem sets. Now we will get to the thing that everybody wants.
Can I ask a quick question about the, so basically you're just talking about the different instantaneous rates of change?
Yes.
Okay.
Exactly. So chapter 3 is where we escape the limit definition of the derivative by learning some basically algebra rules that allow you to go around the limit. The first section here is on derivatives of polynomials and exponential functions. Which are the only functions anybody really wants to deal with. Keeps drifting out of focus. That's irritating. In order to differentiate polynomials, we're going to come up with a rule for differentiating powers of x, and we're going to come up with rules that allow us to split up derivatives. So first, let me relay to you a few theorems. And this is combining derivatives. If little f and little g are differentiable, and I define two new functions, capital F of x is little f of x plus little g of x, and capital G I'll call c times little f of x, where c is a constant. Then capital F primed of x, which would be the derivative of little f plus little g, like this, little f plus little g, all primed. This is a convenient notation. It's the first time we're seeing this. So if you want to write the derivative of some stuff, it is often very nice to just write all that stuff in parentheses with a prime. There is another notation for this that I'll show you called operator notation. This can be done how you would hope. You just differentiate each of the little functions and add them up. This is little f primed plus little g primed. So if you have two functions added up that you want to differentiate, and you know how to differentiate each one on their own, then you can just take each little derivative and add the result. Leave some space over here in your notes, because I'm going to show you an alternate notation, or maybe leave a little space right down below. That'll be better. Yeah, leave some space below. And then underneath that space, capital G primed. And remember what capital G is. Capital G is just the constant c times little f of x So capital G primed would be all of that primed, having had its derivative taken. This is just going to be C times little f primed. So if you want to differentiate, if you know how to differentiate a function, but you want to differentiate 2 times that function or 10 times that function, then the constant just comes along for the ride. All right, you just differentiate the function multiplied by the constant. In other words, constant multiples pop out of derivatives. These two rules together express what is called linearity. And the word linearity has the word linear in it. So you should be thinking of lines right now, but that's not what we're talking about. We're not saying that derivatives have any, how do I say this? We're talking about linearity of a certain kind of special function called an operator. So I'm going to show you the operator notation for each of these. Basically, you can think of the prime as a command. What it does is it takes in a function and it spits out its derivative. The two men who first discovered calculus discovered it independently, and they had their own notation for it. The prime notation is closer to what Newton used. The other man who independently discovered calculus was named Leibniz, and his notation was in terms of operators, which is a little bit closer to what modern mathematicians would prefer in this sort of scenario. So instead of writing a big prime here, you can put the symbol d divided by dx out front. This says, take the derivative with respect to the variable x. This thing is called a differential operator. And you can write the result as follows. Like this. So f prime can be written as df dx. G prime can be written as dg dx. Or the third way of writing this, and I know it's a lot of notation, would be d dx of f of x plus d dx of g of x. So again, d dx just means take the derivative of the thing next to me. And I like reading this equals this, because what it says is you can distribute the operator d dx. If you compare just those, it says d dx applied to a sum of two things is the same as the sum of those two things with d dx applied to each on their own. The bottom one would be written as d dx of c times little f of x equals c times df dx, or I'll write it like that for consistency, c times d dx of f of x. And again, I think it is nicest in the operator notation when you think about just these outer things being equal. But those are all notations that we use to describe derivatives. This looks way more complicated than it is. It just says constants pop out and you can split up over addition and subtraction. That's all it says. Before we get into the power rule, I want to some terminology. The object ddx is called a differential operator. It's a function, but it's a function that takes in functions and spits out functions. And we call those operators. ddx of some input function f of x is equal to some output function the derivative f prime of x. So when you apply ddx to a function, what you get is its derivative, f primed. And sometimes you'll see dy dx, which is even more confusing because like we don't have enough fucking symbols for this shit already. But there is a little bit of utility to thinking about this notation, df dx, dg dx, dy dx, because you can think of if we're thinking about the graph y equals f of x, then dy dx is sometimes written for f primed of x. And you know this is a slope, right? If you plug in any particular x value here, you get the slope of the tangent line. And we can think of dy and dx as infinitely small rises and runs. Dy is the infinitesimal rise, and dx is the infinitesimal run. Now, dy and dx on their own are not numbers. And that's just one of the many reasons why I will use the prime notation at every opportunity and avoid the Leibniz notation for the most part. But they are objects. They can be thought of as infinitesimals, sometimes called hyperreal numbers. Or if you're thinking geometrically in the way that Einstein did, these would be what are called differential one forms. On their own, dy and dx are not numbers. So this is not a fraction in the usual sense. But when you divide a very, very, very small thing by another very, very, very small thing, as long as they are similar in their smallness, you get a normal sized thing. So dy dx as a ratio does make sense, even though dy and dx individually are too small to talk about as though they are numbers. So I just wanted to introduce this notation because this theorem is much better described in that notation, saying ddx of f plus g is ddx of f plus ddx of g, and ddx of c times f is c times ddx of f. When I say that the derivative is a linear operator, I'm saying that this thing, ddx, the differential operator ddx, as studied as a function whose inputs and outputs are both functions, that thing, ddx, is linear. That's what we mean. So it's a big deal in higher math. It's not a huge deal for us, but you do need to know these rules, right? Derivative of a sum is the sum of the derivatives. Derivative of a constant multiple is the constant multiple of the derivative. That's all. And when you see us use it, you'll be like, oh, that's really simple. So first, let me show you the power rule, and then I'll show you an example where we combine the power rule with that theorem. This is your first big differentiation rule. What this says is if f of x is equal to x to the n, then f primed of x is n times x to the n minus 1. Or in Leibniz notation, d dx of x to the n is n x to the n minus 1. A quick proof. This is probably the most important theorem we're going to do all semester, so I do need to prove it for you quickly. I promise it won't be big. I will just give it as simply as I can. F prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. My function f of x here is x to the n, so this is x plus h to the n minus x to the n all over h. N here could be any positive integer. In fact, you'll see that this works even if n is a negative integer or any real number. But when I expand this out, I'm going to assume n is a positive integer to simplify. And I'm not going to show you the full expansion. What we're going to do here, I'm technically using the binomial theorem. That's rarely seen in pre-calculus, but ideally would be. This would be the sum from k equals 0 to n choose k, x to the k, h to the n minus k. You don't need to know what that means. It just means that this starts out with x to the, well, I'll write it like this, x to the n plus x to the n minus 1 times h plus other stuff. With powers of x and h. So this is a system for foiling out really big things, right? Like x plus h cubed is x cubed plus x squared h, or 3x squared h plus 3xh squared plus h cubed. Oh, I'm sorry, and there's an n here. Right here. So you can skip the blue entirely if you want. You can just say, I'm using the binomial theorem, and then look that up in your own time if you want. As I expand this out, I'll get x to the n plus n x to the n minus 1 times h plus the next term here would be n choose n minus 1, choose 2, which is n times n minus 1. So we'll say like this is other terms with h squared and higher. And then I still have my minus x to the n. And downstairs here, I still have my h. So the idea is that the power of x goes down by 1 every term in this expansion, and the power of h comes up by 1 every term in this expansion. So if you were to FOIL this out, if this was like x plus h to the 5, the first term would be x to the 5. The second term would be 5x to the 4 times h. And then the other terms after that would have higher powers of h and smaller powers of x. The good news here is that x to the n cancels. And then I'm left with lim h to 0 and x to the n minus 1 times h plus other terms with h squared and higher all over h. This term right here has an h, and all of the terms in here that I'm not writing have h's, not just h's, but h squared and higher. So I can factor an h out from the top. And what's left here is nx to the n minus 1, and then plus other terms. I factored out an h, so this is with h and higher. H to the 1 and higher. And all over h. Cancel the h's. Since all of these terms have at least h to the 1 in them, all of these will go to 0 as h goes to 0. So you really do just get nx to the n minus 1, which is what we wanted to prove. At the end of a proof, it's customary to put it's called a tombstone, a little square. So we're done. Okay, I invite you to look into the binomial theorem. You want to talk about this stuff in detail, you can do it in office hours, Canvas messages, wherever, or the internet has tons and tons and tons of good things, but that's not what I'm here to beat you up about. I want to show you how to use this rule. And the main point of this rule is that to differentiate a power of x, bring the power down, reduce the power by 1. That's it. Derivative of x to the n is nx to the n minus 1. So for example, if f of x is the square root of x, find f prime of x. We actually did this earlier, remember? We got 1 divided by 2 times the square root of x. We did it using the limit definition. It was kind of a pain. We had to multiply by the conjugate, blah, blah, blah. No más. F of x is x to the 1/2. So n is 1/2. Which means by the power rule, f prime of x should be 1/2 times x to the 1/2 minus 1. Right? N times x to the n minus 1. And here is 1/2. Just applying the power rule. 1/2 minus 1 is negative 1/2. So I get 1/2 times x to the negative 1/2. Which is 1/2 times 1 over x to the 1/2. Right, x to the negative 1/2 here is 1 over x to the positive 1/2. And if you take that and write it as the square root, you get this, which is what we saw earlier today, just using the limit definition. Isn't this nicer? Oh my God, it's so much faster. It's so much faster.
Can we use the power rule in exams, or do you want us to like?
So this is what I was saying earlier. If the problem says you have to use the limit definition, then you must use the limit definition. But if it doesn't, if it just says find this derivative, then yes, and please do, right? So the only time you should whip out the limit definition for a derivative calculation is if you're specifically told to. Otherwise, use the rules, right? Save the time. Okay, a simple, straightforward example. Let's see one where we combine this with the previous theorem. What you'll see is that you can differentiate all polynomials this way. If f of x is, say, 6x cubed minus x to the 4 plus 2x squared, say, minus 1 over x cubed. Find f prime of x. Now this is not technically a polynomial because this last term here has an x downstairs. But if I just had those first three terms, that would be a polynomial. And the big idea from that theorem is that you can differentiate each of the pieces on their own. So first I'm going to rewrite f of x in a form that is useful. The only thing I need to be careful about here this last term, I'm going to write as minus x to the negative 3. And now some practice with Leibniz notation, since it is the better way to describe. Well, let's stick to the prime notation. So f primed of x. Nah, we use Leibniz. We'll use it. We'll do it. We need the practice. What that very first theorem of this section tells us is that I'm allowed to split this stuff up. So according to that theorem, that is 6 times d dx of x cubed minus d dx of x to the 4 plus 2 times d dx of x squared minus d dx of x to the negative 3. So if I want to take the derivative of this sum of power functions, I can do that by taking the derivative of each piece on its own. And then each of those pieces, any constant multiples will pop out. The negatives are constant multiples, right? That is a factor of -1. So he pops out according to the second part of our first theorem. Now by our second theorem, each of those derivatives can be calculated from the power rule. 6 times this derivative, d dx of x cubed, that's x to the n, so that's 3x to the 3 minus 1 is 2. Minus is this minus, d dx of x to the 4 is 4x to the 3, right? And x to the n minus 1. You bring down the power and subtract 1 from the power. Plus 2 times d dx of x squared, that is 2x to the 1. And then minus d dx of x to the negative 3 would be negative 3 x to the negative 4. And be careful, if it's negative, subtracting will make the power more negative. right? -3 minus 1 is -4. So what we get here is 18 x squared minus 4 x cubed plus 4x plus, I'll write this as 3 over x to the 4. So the important steps here are take this guy and split him up, popping everybody's constants and negative signs out. And then each of these little pieces is a power rule derivative. So for each of those little pieces, like here where n is 3, you get n x to the n minus 1. So when n is 3, x cubed becomes 3x to the 3 minus 1 is 3x squared. X to the 4, when that n x to the n minus 1 is applied, you get 4x to the 4 minus 1, or 4x cubed. The rule couldn't be simpler. It's actually very, very nice, right? Once you get comfortable with it. Usually when you take derivatives like this, you will not write out all these steps. Usually you would just jump to this. Okay. We've gone a little bit over, right? It was 2 to 3:15, right? So I've taken up enough of your time. I will go ahead and stop here. I'm going to publish a new homework set for you today, which has you working with these derivative rules. Quick note, we can now differentiate all polynomials and power functions quickly. And there are other functions that you can rewrite like that. If I wanted to differentiate something like x squared minus 2x over the square root of x, we don't have a rule for differentiating fractions yet. But you can split this up. So it's x squared over root x minus 2x over root x. Simplifying here, this is x to the 2 divided by x to the 1/2. So that would be x to the 2 minus 1/2, which is 3/2. X to the 1 divided by x to the 1/2 would be x to the 1/2. And then you could apply the power rule. So that would be 3/2. X to the 3/2 minus 1 is 1/2. Minus 2 times 1/2. X to the 1/2 minus 1 is negative 1/2. So we would get here 3/2 x to the 1/2 minus x to the negative 1/2. So the fact that we can differentiate polynomials should be evident. The fact that we can differentiate power functions and combinations of polynomials and power functions should be evident. Some things are not obvious combinations of polynomials and power functions, like this. Anytime your denominator is a single term, you can play this game where you split up the fraction like that. And it's a powerful tool for saving you time. Down the road, I will give you a rule for differentiating fractions like this. In fact, next time we're going to talk about the product and quotient rules. But you don't want to use that shit unless you have to, because they're messy. So anytime you can do algebra to clean things up first, that's the message I wanted to send you away with. Anytime you can simplify before doing the calculus, right? Before taking your derivative, even if you're just trying to use one of these basic rules, simplify first, all right? Your finger calluses will thank you. You'll end up writing considerably less. That's it from me for today. I hope you guys enjoy not having to do all those limit calculations and the future derivative work. Do make sure you practice the limit calculations. If you have not finished that previous homework set, don't solve those problems using the power rule. Do the right thing. Make sure you can do the limit calculations. Otherwise, it'll bite you on the test, because if you don't do that when I tell you to, I won't give you credit. But that's it. I'll take good care, guys, and I'll see you all on Wednesday.